Monty for giving me the opportunity to present my work, whose main idea, as we'll see, is to settle a unified geometric framework for the propagation of waves under very general conditions. There is a work in collaboration with Miguel Ángel Jabaloyes and Miguel Sánchez, and every result I'm going to talk about can be found in these references. The first one settles this general framework, and the second one is an application to wildfires that we are currently working on. Miguel Ángel has already talked about this briefly in the Finsler mini course. Well, here I'll try my best to explain the main ideas in more detail. So in this talk, I'll begin by giving the physical motivation behind this work, how we can establish the mathematical setting. Then we'll see what Huygens' principle tells us about the propagation of waves, which will lead us to the specific differential equations that provide the wavefront. And finally, we'll apply all of this to the case of wildfires. So let's begin with the motivation. Assume that a wave is propagating on an n-dimensional manifold, although for computations we'll work in coordinates in a subset of Rn. And our goal is, given the space of velocities of the wave, which we call sigma, and this is given a closed curve in each tangent space that yields the velocity of the wave at each point and for each direction, we want to find how the wave propagates over time. And we want to find this propagation in the most general situation where we allow the velocities to be anisotropic, which means that they depend on the direction, such as in this case. And this is the reason why our problem turns out to be Finslerian. And we also allow the velocities to be rheonomic, which means that they are time dependent. And this motivates us to consider a temporal dimension and see the propagation of the wave within this space-time. Now, given this situation, this is the first result we have to take into account. If for each point of the space-time, this closed curve, which is included in the tangent space to n for a fixed time, if it is diffeomorphic to a sphere, strongly convex, encloses the zero vector, and varies smoothly, then sigma is the indicatrix of a time-dependent Finsler metric on n. So under very reasonable conditions when dealing with waves, for example, this case satisfies all of these conditions, the velocities of the wave are given by a Finsler metric. And once we have this metric, then this G becomes a Lorentz-Finsler metric on M, which makes our space-time be a Finsler one, in the same sense as Miguel Ángel explained before. Now, our choice, the choice of this metric is because a curve parameterized by time has the same velocity as the wave if and only if it is light-like for G. So we have basically built a Finsler space-time where the propagation of the wave is given by light-like curves. This idea is represented here. If the wave started at a single point, P, then its propagation would be given by the causal future of P. Now we have an initial wavefront of this form, being S a compact embedded submanifold of codimension R in N. Then Huygens' principle tells us that its point of the initial wavefront behaves as a source in itself. So the wavefront at time t0 is going to be given by the envelope of all these secondary waves of labs t0. And this is the boundary of the causal future of the initial wavefront when intersected with the slice at constant time t0. So we will know how the wave propagates by finding this boundary. And to this end, we have these results. The first one is very well known in Lorentzian geometry, and here we extend it to our Finslerian setting. It says that the only causal curves from S0 included in this boundary are the light-like geodesics departing orthogonally from S0 until they arrive at their cut points. This is until they no longer minimize propagation time. So for example, this curve here, which is entirely included in this boundary, must be a light-light geodesic orthogonal to S0. And the moment it arrives at its cut point, and this happens when it meets another light-light geodesic from S0, it leaves the boundary and therefore it no longer provides the wavefront. But we also have this crucial theorem, which is very delicate even in the Lorentzian case, because the properties of the cut points from an arbitrary submanifold are not fully studied. And in fact, in our work, we provide an independent proof for Finsler spacetimes. And it basically says that there exists a small time before which no light-light geodesic orthogonal to S0 arrives at its cut point. And then, as an immediate consequence, at least for a small time, this is a hypersurface of M foliated by all the light-light geodesics orthogonal to S0. Therefore, in order to compute the wavefront, we have to find these geodesics. But first, we need a way to parameterize all of them. So consider now the normalized light-like orthogonal bundle to S0, which is composed of all the vectors of this form, which are light-like and orthogonal to S0. It can be proven that this is, locally, this is diffeomorphic to S cross the sphere of dimension r-1. Remember that r is the codimension of S in N. So each vector here can be expressed as a point in S and a direction in the sphere. And now we can define what we call the wave map as this three-parametric map between the parameters the time, the position in the initial wavefront, and the direction, satisfying that the curve of parameter t is the unique time parameterized light-like geodesic whose initial velocity is light-like and orthogonal to S0. What the wave map does is mapping this boundary. For example, in this case, S0 is a hypersurface of N. So we have this situation. There are only two light-like orthogonal directions, one going outwards and the other going inwards. I'm fixing a point in the initial wavefront and a direction. Then this curve of parameter t represents a space-time trajectory of the wave. Its projection represents a spatial trajectory of the wave. I'm fixing a time t0, then these curves of parameter s provide the wavefronts at that time. So we have reduced our initial problem to the computation of this wave map, which by definition is going to be given by the geodesic equations of the Finsler spacetime when reparameterized by time. And this is basically what this theorem tells us. For each light-like and orthogonal direction, the wave map written in coordinates is given by this ordinary differential equation system, where here I'm using Einstein's summation convention. And these gammas are the so-called formal Christoffel symbols, which play the same role as the usual Christoffel symbols in Lorentzian geometry, with the difference that here they depend on the direction. And specifically, this denotes the velocity of the space-time trajectories of the wave. And the initial conditions are the ones expected. The initial position is the initial wavefront, and the initial velocity must be light-like and orthogonal to S0. So we have seen so far that this geometric framework removes the usual restrictions of isotropic and time-independent propagation. There is also another problem that it naturally solves, which is the strong wind case. This is a situation when the medium moves faster than the wave. Think, for example, of a sound wave and a wind so strong that it completely drags the wave with it. And what happens in this case is that sigma doesn't enclose the zero vector, and therefore it doesn't define a Finsler metric, but a conic Finsler one. And this makes the problem much more complicated from the point of view of the space. However, from the space-time viewpoint, we don't have such a drastic change. It's just a matter of tilting the cones. And in fact, we still have a Lorentz-Finsler metric. So we can compute the wave map and therefore propagation of the wave exactly in the same way as we did before. So observe that this This space-time viewpoint allows us to solve both the time-dependent problem and the strong wind case without any additional effort, which is a great advantage. And finally, the specific application we are currently working on is the case of wildfires. When modeling wildfires, the space M is a two-dimensional surface embedded in R3, and the initial fire front is a hypersurface of N. So we basically have the same situation as before. There are two light-like orthogonal directions, but now we are only interested in the wavefront going outwards because the inward region is usually assumed to be already burned. So we can draw the dependence on the direction in the wave map, and fixing a point in the initial fire front and varying t, we obtain the spatial trajectories of the fire, which are these red curves. And fixing a time and varying s, we obtain these transversal curves, which are the fire fronts at different times. In our model, we use Matsumoto metric as the Finsler metric that provides the velocities of the fire. And this metric models the fact that when there is a slope, the fire moves faster in the upward direction. And as a final remark, remember that these geodesics only provide the wavefront as long as they don't arrive at their cut points. But what happens when such a point appears? Well, the wave map can still be computed. In fact, it always provides the wavefront at any time. But after the first cut point, we have to be more careful because the wavefront is not going to be given by all the geodesics, but only by those which haven't arrived yet at their cut points. For example, this is a situation one usually encounters when modeling wildfires. Here we have two spatial trajectories that meet at different points. And what happens in this case is that the trajectory that arrives later is reaching a point that is already burned. So it cannot be in the fire front. This means that this curve has already passed its cut point, and therefore it must not be taken into account in order to compute the fire front at later times. On the contrary, the trajectory that arrives earlier keeps providing the fire front after encounter and until it reaches its own cut point. And to conclude, here I show you some further references. The first one is a work by Professor Mark Borsen that, as far as I know, was the first one to model the propagation of wildfires using Finsler geometry. In this one, he also solves the time-dependent problem, although without using space-times. There is a later work by Professor Gibbons that also includes applications to wildfire modeling. And in this one, you can find all the background regarding Lorentz-Finsler metrics, Finsler spacetimes. And that's all I wanted to tell you. Thank you very much for your attention.